NFPA 70, the National Electrical Code, Article 250.174 requires periodic testing of the effectiveness of grounding systems. Section 250.174 specifically mentions periodic tests for grounding systems in hazardous classified locations. ANSI/TIE 222G, the Telecommunications Infrastructure Standard for Grounding, Bonding, and Surge Protection, Section 10.32 requires annual testing of grounding and bonding systems in areas designated as Class 1, Division 1 or Division 2. The testing shall include verification of the potential to ground. Other codes and standards such as OSHA, the Occupational Safety and Health Administration regulations may also require periodic testing of grounding systems in hazardous locations. IEEE Standard 142, Grounding of Industrial and Commercial Power Systems, recommends testing the potential to ground of grounding circuits in hazardous areas on a regular basis. Additional considerations include the frequency of testing, which may vary depending on the type of facility, environmental conditions, and other factors. Testing should be performed by qualified personnel using appropriate test equipment. Test results should be documented and maintained for future reference. In summary, there is a requirement to test the potential to ground of grounding circuits in Class 1, Division 1 or 2 areas, towers, and similar locations. This requirement is found in multiple codes and standards, including NFPA 70, ANSI/TIE 222G, and IEEE Standard 142. The frequency of testing may vary, but annual testing is recommended for areas designated as Class 1, Division 1 or Division 2. To elaborate further on NFPA 70 Article 250.174, it's crucial to understand the scope. This article addresses grounding requirements specifically for separately derived systems in hazardous locations. A separately derived system is an electrical power source, such as a generator or transformer, that is not electrically connected to the building's main power supply. In hazardous locations, the grounding of these systems is particularly important for safety. The periodic testing mandated by Section 250.174 is designed to ensure that the grounding system remains effective over time. This effectiveness can be compromised by factors such as corrosion, loose connections, or physical damage to the grounding conductors. The testing should verify that the grounding impedance is low enough to facilitate the rapid clearing of ground faults, thereby minimizing the risk of electric shock and fire. Moving on to ANSI/TIE 222G Section 10.32, it's important to recognize that this standard is specific to telecommunications infrastructure. Towers and other telecommunications structures are often located in exposed environments, making them particularly vulnerable to lightning strikes and other electrical hazards. The annual testing requirement in this section is intended to ensure that the grounding and bonding system can effectively protect equipment and personnel from these hazards. Verification of the potential to ground involves measuring the voltage difference between the grounding system and the surrounding earth. A low potential difference indicates a good grounding connection, while a high potential difference suggests a problem with the grounding system. The standard provides guidance on acceptable potential difference limits. OSHA's regulations regarding grounding in hazardous locations are typically found in 29 Code of Federal Regulations 1910.304. These regulations require employers to ensure that electrical equipment in hazardous locations is properly grounded to prevent electrical shock hazards. While OSHA does not explicitly mandate a specific testing frequency, it does require employers to conduct regular inspections and maintenance of electrical equipment, which should include verification of the grounding system's integrity. IEEE Standard 142, also known as the Green Book, provides recommended practices for grounding industrial and commercial power systems. It offers detailed guidance on the design, installation, and testing of grounding systems. While the Green Book is not a mandatory standard, it is widely recognized as an authoritative source of information on grounding practices. The recommendation to test the potential to ground of grounding circuits in hazardous areas on a regular basis reflects the importance of maintaining a low impedance ground path in these locations. The frequency of testing should be determined based on a risk assessment that takes into account factors such as the type of facility, the environmental conditions, and the criticality of the equipment being protected. When determining the frequency of testing, several factors should be considered. Firstly, the type of facility is crucial. For example, a chemical plant or refinery may have a higher risk of electrical hazards than a warehouse or office building. Secondly, environmental conditions play a significant role. Corrosive environments such as coastal areas or industrial sites with airborne pollutants can accelerate the degradation of grounding connections. Thirdly, the criticality of the equipment being protected should be taken into account. Equipment that is essential for safety of production should be tested more frequently than equipment that is less critical. Qualified personnel should perform testing using appropriate test equipment. This equipment may include a ground resistance tester, a clamp-on ground resistance meter, and a voltmeter. The ground resistance tester injects a test current into the grounding system and measures the resulting voltage drop to determine the ground resistance. The clamp-on ground resistance meter measures the ground resistance without disconnecting the grounding conductor. The voltmeter is used to measure the potential difference between the grounding system and the surrounding earth. It is essential to document and maintain test results for future reference. This documentation should include the date of the test, the location of the test point, the test equipment used, the test results, and the name of the person who performed the test. The documentation should be reviewed periodically to identify any trends or anomalies that may indicate a problem with the grounding system. Furthermore, the test results should be compared to previous test results to assess the condition of the grounding system over time. A significant increase in ground resistance or potential difference may indicate a deterioration of the grounding connection or a fault in the grounding system. When performing grounding tests, it's important to follow proper safety procedures. Firstly, ensure that the equipment being tested is de-energized before making any connections to the grounding system. Secondly, use appropriate personal protective equipment, such as gloves and safety glasses. Thirdly, be aware of the potential for step and touch potential hazards, especially in outdoor locations. Step potential is the voltage difference between 2 points on the ground that can be touched by a person's feet. Touch potential is the voltage difference between a grounded object and the surrounding ground that can be touched by a person's hand. To minimize these hazards, stand on an insulating mat and avoid touching any grounded objects while performing the tests. Grounding is essential for electrical safety, especially in hazardous locations. Grounding provides a low impedance path for fault current to flow back to the source, which causes the overcurrent protection device, such as the circuit breaker or fuse, to trip and de-energize the circuit. This minimizes the risk of electric shock and fire. In addition to providing a path for fault current, grounding also helps to stabilize the voltage of the electrical system. This is particularly important in hazardous locations, where voltage fluctuations can increase the risk of ignition. Proper grounding can also reduce the amount of electromagnetic interference, EMI, generated by electrical equipment. EMI can interfere with the operation of sensitive electronic devices. Grounding systems should be designed, installed, and maintained in accordance with applicable codes and standards. These codes and standards provide detailed requirements for grounding conductors, grounding electrodes, and bonding connections. Regular inspections and testing of grounding systems are essential to ensure that they remain effective over time. The National Electrical Code, NEC, provides comprehensive guidelines for electrical installations, including grounding and bonding requirements. Article 250 of the NEC covers grounding and bonding in detail. It specifies the types of grounding electrodes that are permitted, the sizes of grounding conductors that are required, and the methods for bonding metal parts of electrical equipment. The NEC also addresses grounding requirements for specific types of equipment and installations, such as generators, transformers, and hazardous locations. It's essential to consult the latest edition of the NEC for the most up-to-date grounding requirements. ANSI/TIA standards provide requirements for telecommunications infrastructure. ANSI/TIA AMINUS 607 series addresses grounding and bonding requirements for telecommunications systems. These standards specify the types of grounding and bonding conductors that are required, the methods for connecting grounding and bonding conductors, and the requirements for grounding electrodes. The ANSI/GIA standards also address grounding requirements for specific types of telecommunications equipment, such as servers, routers, and switches. It's important to consult the appropriate ANSI/GIA standard for the specific type of telecommunications system being installed. IEEE standards provide recommended practices for various aspects of electrical engineering, including grounding. IEEE Standard 142, the Green Book, provides detailed guidance on the design, installation, and testing of grounding systems. The Green Book covers topics such as grounding electrodes, grounding conductors, bonding connections, and ground fault protection. IEEE Standard 1100, the Emerald Book, provides recommended practices for powering and grounding electronic equipment. The Emerald Book covers topics such as grounding, bonding, shielding, and power quality. These IEEE standards are valuable resources for electrical engineers and technicians who are responsible for designing, installing, and maintaining grounding systems. OSHA regulations require employers to provide a safe workplace for their employees. These regulations cover a wide range of hazards, including electrical hazards. OSHA regulations require employers to ensure that electrical equipment is properly grounded to prevent electrical shock hazards. OSHA also requires employers to train their employees in the safe use of electrical equipment and the hazards associated with electricity. Employers should consult OSHA regulations to ensure that they are in compliance with all applicable requirements. In addition to the codes, standards, and regulations mentioned above, there are also several other resources available that can provide guidance on grounding and bonding. These resources include manufacturers' instructions, industry best practices, and training courses. Manufacturers' instructions provide detailed information on the proper installation and use of electrical equipment, including grounding and bonding requirements. Industry best practices represent the collective knowledge and experience of experts in the field. Training courses provide instruction on the principles of grounding and bonding, as well as practical skills for installing and testing grounding systems. By consulting these resources, electrical engineers and technicians can ensure that they are following the best practices for grounding and bonding. Furthermore, consider the specific requirements for Class 1, Division 1, and Division 2 locations. Class 1 locations are those in which flammable gases or vapors are or may be present in the air in quantities sufficient to produce explosive or ignitable mixtures. Division 1 locations are those in which hazardous concentrations of flammable gases or vapors are likely to exist under normal operating conditions, or where hazardous concentrations may exist frequently because of repair or maintenance operations or because of leakage. Division 2 locations are those in which hazardous concentrations of flammable gases or vapors are not likely to exist under normal operating conditions but may exist accidentally. The NEC provides specific requirements for electrical equipment and wiring in Class 1, Division 1, and Division 2 locations. These requirements are designed to minimize the risk of ignition in these hazardous environments. It is crucial to select electrical equipment that is rated for the specific class and division of the hazardous location in which it will be installed. Equipment that is rated for a higher class or division may be used in a lower class or division location, but equipment that is rated for a lower class or division may not be used in a higher class or division location. In addition to selecting appropriate electrical equipment, it is also important to follow proper installation practices. All wiring in Class 1, Division 1, and Division 2 locations must be installed in rigid metal conduit or in cable with a gas-tight continuous metallic sheath. All conduit and cable fittings must be explosion-proof. All electrical connections must be made in explosion-proof enclosures. These installation practices are designed to prevent the escape of flammable gases or vapors from the electrical system. Regular inspections and maintenance of electrical equipment in Class 1, Division 1, and Division 2 locations are essential to ensure that the equipment remains in safe operating condition. Inspections should include a visual examination of the equipment for any signs of damage or deterioration. Maintenance should include tightening connections, lubricating moving parts, and replacing any worn or damaged components. It is also important to test the grounding system regularly to ensure that it is functioning properly. The frequency of testing should be determined based on the specific conditions of the hazardous location. Grounding and bonding play a critical role in ensuring electrical safety in all locations, but they are particularly important in hazardous locations. By following the codes, standards, regulations, and best practices described above, electrical engineers and technicians can help to minimize the risk of electrical hazards in these environments.